Hi everybody, welcome to our tutorial about waves. Until now, we was talking about electro effect, right? Electricity and stuff, and then magnetism, and we see that they are involved in each other. But right now, we're taking a break. We're stopping. We started to talking about other phenomena, which called wave. And waves is actually a jungle, a zoo, another topic, not related, not related to the class. It could be a different class separated on its own, the physics of wave. When you're talking about the ocean, wave in the ocean, they're moving, or when somebody is singing, he's actually sending the waves to you. And also light is a wave, okay? So this can describe a lot of stuff, but what actually makes wave and why do we need it? So the introduction for that is actually telling you that electromagnetism actually so connected to each other. We're going to see it in a wave phenomena in the next class. So let's describe better what is a wave. Wave is a disturbance, okay? Something that they do that disturb the world. And this disturbance actually can go and propagate, okay, in space, but also in time. So let's write the equation. That if this equation describes the phenomena is going to be a wave phenomena. Okay, this is the rule. So the equation is looking like this. This function, f, is my disturbance. Disturbance. And disturbance can be many things. It can be changing pressure. It can be some piece of ocean that's actually moving, some contraction in a spring, some disturbance, something that is changing, okay? And this one, if it's changing by the time square, derivative by times twice equal to velocity. This is the velocity of the disturbance, velocity. And in our class, we're gonna deal with constant velocities, okay? We're gonna do, simplified case of waves. And here we're gonna have another derivative, which is the x derivative. So if you apply and use this equation, if this is hold to your case, if you derive the disturbance in space twice, multiply by its speed and get this thing, you're actually in a wave phenomena. This is the concept, this is the idea. And I want to give a few examples. Think about a wave in the ocean, okay? So the world peaceful, you have like a flat ocean, nice ocean, for sailing day, and then coming a big wave, a tsunami coming in. This is a disturbance, and it's moving in the x direction, space, and it's changing its location in time. So this is a wave phenomena, classical wave phenomena. Another phenomena is voice, is singing. For example, if I'm in the library, it's really silent and peaceful, and then I'm shouting something. So I actually make myself, my body, my vocal box actually made a disturbance. Yes, question? What? V, yes, thank you very much. V squared, perfect. So V squared? Yes, V squared, yes. Perfect, yes, units, makes sense, thank you. So if I'm in the library, so my vocal cord can actually produce a disturbance in space and in time to propagate this one, and I can sing suddenly and do something, and this propagate to your ears, right? Perfect, so that's the idea. And as I told you before, we're gonna do a simple case of a constant velocity, right? So what is the equation for a constant velocity? X equal vt, right? The time that I'm walking, the speed that I'm walking equal to the distance that I made. So we're gonna take this equation and change it a little bit to our own needs. That's the idea. So if I'm looking at this equation, so I want to talk about an oscillatory disturbance. What do I mean? If, for example, I'm clapping my hands, right? So I actually made a disturbance. But if I'm gonna do that, disturbance, and I can count how much time I'm taking between each one. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So this actually can be changed. If I want to talk about only one period, I can talk about capital T, which this is what? The time period, right? How much time I'm taking between each oscillation. And here, I want to talk about what is this distance. So if, for example, I clap in my head, I actually compress air. This is the disturbance. I take the air and lock it in, small space, and send it to the wall, right? It's going all direction, but let's stop only in the X direction. For example, your ear is over there. So I'm clapping, and this one is going. So 1, 2, 3, 4. 1, 2, 3, 4. So this distance that I make in the 4th second, for example, is actually called lambda. And this is the name, the formal name is the wave length. So this is the length that the propagation is succeeding to go in this time, okay? And from here, I can take the equation to 2 different scenarios that are really, really famous and useful. The first one is, you know, I did not must talk about period, right? Sometimes it's talking about how much, what is the rate, right? What is the tempo that they do it, right? So instead of talking about 1, 2, 3, 4, 1, 2, 3, like I said, dude, you clap 20 times in 1 minute, right? So this is a frequency, okay? How much time you clap in a single, in a specific time. So this is like the tempo, the rate, okay, the frequency that this phenomena happens. So what is the connection between time period and frequency? Yes, it's 1 over, so 1 over t is actually equal to the frequency. Okay, so I can take this one, and this is more useful when talking about waves, talking about the frequency, that we see this propagation happens, and this equation becoming this one, v divided by f, and most of the time, our interest is what is the velocity of the propagation. This is what makes really interesting properties. So this one equal to that. So this is another famous equation like this, okay, for waves. And I told you, I promise you, there's other ways you can take this equation. What is the other way? I have a space here. They see me on the board? Okay, so here I can take this one to another phenomenon. I wanted to think about, this is a little bit more abstract, but let me make it simple, okay? For example, period, okay? People love to think about period things in a circle. Think about the time. The day is a period phenomenon. And how we describe it by circle, right? The time. We said this is how much time you have the sun, right? Finish one round and then we're going to darkness, right? So this is the idea. So people feeling more intuitive talking about circles instead of propagation in space. It's made for us more intuitive sense. So now let's go to this board. So I'm taking this equation, V, T, and I draw this circle, okay? And like we have a clock, right? We have a clock, and we have some angle theta, right? So I can understand where I am. For example, here I clap my hand, right? Clap. 1, 2, 3, 4. 1, 2, 3, 4. 1. It's easier to understand the phenomenon by just looking at the circle, right? So that is the concept. So what I'm gonna do, I want to correct this one. I want to change this one a little bit. And what I'm gonna actually do, I'm gonna divide by this and divide by that. So what I mean, I'm gonna have 1 over t equal to v 1 over lambda, okay? And now we're gonna multiply by 2 pi, mean the whole thing, right? So look at these 2 ratios. That's what I want you to see. These 2 ratios are gonna be really interesting. This one get 2 pi over t equal to v 2 pi over lambda. So what I actually have here, what is this? Remember this one? Familiar to you? Radians per second. This is how fast I am moving on this line. This is omega, radian per second, right? This how much angle I'm succeeding, this is per second, I succeeded doing in the time that I was given. So this one is actually omega, right? Radian per second. And here I have V, nothing special about here. This is how much meters did I go how much meter did I go in this specific time. And this one is a new thing that you never saw before, but I want you to understand that this one is easy. It's not complicated. Why it's easy? Because it's the same concept like this one. Instead of talking about time, it's talking about meters, okay? So how much meters did I go, where I am, and what is the angle that actually applied to this distance that you go? For example, I did half of the way. I did 2 meters, not 4 meters. Ah, dude, you are here in the cycle. You understand? You are at pi. I finished I did my 4 meters, okay? So, dude, you finished, so you are here, you are at 2 pi. You understand the concept? It's compared, not time to an angle, it's compared distance to an angle. Understand? So this one is called the wave number, K. Wave number, okay? So this is really important equation, okay? So we have this important equation, wave number, and what's the unit of the wave number? What? No, not 1/meter. It's a common mistake. Even in books, it's a common mistake. It's radian. Yes, thank you very much. It's a radian per meter, okay? It's really important. This K is kind of not real. It's living this imaginary cycle. The clock is not real. The clock is not real, right? The sun going over Earth, it's real, okay? The trajectory the sun is doing is real. But this cycle is just a way for us, people, okay? People with our mind and our capabilities, right? And our limitation to understand better the phenomena. Got it? Okay? So this is important. Take me back to this board. Take me back to this board with the camera. This one is important to us. Really important. And this one is really important to us, okay? So these are the common equation to this subject, okay? So let's clean the board and start our equation, okay? So the question that I prepared to you, it's a really simple question, but it's actually talking about the basic concept of, also going to clean the basic concept of waves. So when I was in the army, I had a really cool headphones. Now everybody have these headphones, right? I'm old, so this technology got cheap, okay? So, but I had the headphones which was actively making making noise cancellation, okay? Which means that I was in the airplane in a military mission, and the engine of the airplane was doing such a hard, heavy noise, and we were on a mission, you know, we had stuff to do, and we need to talk to each other and stuff. So my airborne headphones could cancel out this annoying noise, and then I can hear the people around me. I can do stuff. I can talk with the, you know, in the cellular phone, in the how I call it, Lavian. Never mind. So I can talk to the people in the airplane. There was no problem. So today we're gonna solve a question about active noise cancellation. So this is gonna be our equation. Cancellation. Perfect. Okay. So in my airplane, I hear this. That's the sound that I'm actually hearing. I'm hearing this function. This is the disturbance that the engine is doing, and the engine is doing oscillatory thing, right? That's what it's doing, right? So it's actually producing this sound. You have the amplitude. This is the power, the force that they actually, how noisy it is. Okay, this one. Ouch, dude, what is this engine? So this is called amplitude. Amplitude, okay? Amplitude, and it's multiplied by what? What I want? Oscillatory thing. So what oscillatory tools we have in math? Sinus, for example, sinus. And a question. This must be all the time sinus. It could be cosinus, or it can be, what is sinus? Sinus is actually, I'm starting really weak, and then I become stronger. And then we have the other one, which is cosinus, right? Which what is doing is the opposite. Is I'm starting the strongest and I'm going to disappearing, right? But I actually can have something in between, right? I can have it. It can happen. It's a physics, you know. So what I'm gonna do a space here. So we're gonna write sinus, but it's important to notice that I can correct it anytime that I want to whatever I want by this constant. So this is the phase constant. Phase constant. What? Constant. Okay. So I can actually fix whatever I want. Okay. So now it's a general case, right? Oh, so what's going on here? So here we have your friends. You're already familiar. We have here, it is a solitary phenomena, right? So I want to write here solitary parameters. And I can use the analogy of walking or circle, right? This is the two words. I can do that. Okay? I can tell you the sun is over here. I can tell you the time is 3 o'clock. Both work. You understand what I mean? Both say the same. Okay? So here I'm going to write K, which is the wave what? Wave number. Perfect. This is the wave number. And it's related to the distance that I propagate, right? Perfect. So, and here I'm gonna write V, the velocity. Yes, you got it? V, the velocity. Perfect. And here I'm gonna write, sorry, not V, I'm gonna write X, location in space. Okay? Location at 13. Color, location is dying out. Location is space, right? And I'm gonna do minus VT. That's it. Okay, this is my engine noise. It's a given thing. This is my engine noise. Until here, everything is clear? Perfect. So let's move on with this. And I want to ask you, first of all, is this a wave phenomenon? This function. This is a wave phenomenon? I don't know. What do you think? How we can check if this is a wave phenomenon? One way to do it. Is this hold? If this is holding, this is a wave phenomenon. Go ahead, do whatever you want. It's a wave. So let's check if this is a wave phenomenon, okay? So this is gonna be the first question. Take me over there. Okay, so. Perfect, so I'm here. Wonderful. So is the engine noise is a wave phenomena, right? So how are you gonna do it? Let's do the math, right? So let's derive it by time twice. So I'm gonna take F. I'm gonna take F. F is a. I'm gonna derive it by T, and what's gonna get? I'm gonna get A cosines K X minus VT, right? Plus this phi, this phase, and what's gonna happen to me? Since I derive it by time, these two are actually going out. You see it? These two going out. So I have here minus VK. See? Minus VK. Got it? That's what happened. And now what I want to do? Do it again, right? So I'm going to do it again. So let's derive it second time. Up, up. And we're going to get A stay in place, sin stay in place, K X minus VT plus phi. And right now this one becomes squared, so we got VK squared. Okay? And I wanted to look at the intuition that if I derive it twice, sinus become again sinus, right? So you see the formal equation, go ahead back to here. Go back to here. Yes? Our cameraman is a little bit sleepy, but it's okay. Make you time to process. So you see that if I'm gonna derivative time twice, I'm gonna get back sinus. If you're gonna derive it by x, here x, I'm gonna get Again, sinus. It's going to be sinus, cosine, sinus. So this is make a good intuition. So we found this one. Let's derive it by x twice, right? So I'm going to do it. And I'm going to clean the first one. We don't need it. Okay, so let's derive it by x. Different color. So x and derivative by x equal to what? A cosines, right? The sign is changed to cosines. In the argument, it's gonna be the same, x minus pt plus phi, okay? And multiplied by what? What? What's in front of x? Not minus, just k, right? Just k because it's what's here. And if I'm gonna derive it again, so this one's gonna become sinus, right? If I'm gonna do it, let's do it in different colors. So if we're gonna derive it again, so this one is back to sinus, and this one becoming square. See it? And now, if you're gonna divide both of them, do they the same by only the difference of what? You see it? So if I'm gonna take this one, it's the same as this one, but this k can go out. I can divide by k squared, and I stay with v squared. So, guys, this is a wave phenomena. Good for us. Let's move on. So, the really interesting question is actually how these active headphones can actually cancel out the NG. So, I'm going back to this board. So how does active noise cancellation happen? What does the headphones need to do in order to make it happen? So,
did you miss a minus
question?
sign there? Did you miss a minus sign there?
I don't hear you at all.
Did you miss a minus sign there?
What?
The derivative.
Can you write in the chat, and then we're gonna tell me what you are writing, okay? It's gonna be a better way to do it. So, okay, let's do it. So how does active noise cancel unwanted noise? Okay, so this I'm gonna draw what you're actually hearing. So your ear, this is F, big F, okay? So your ear actually hearing what? The NG, right? So this is this one. Let's call it F1. This is gonna be F1. It's a function of X and T. This is the engine, right? And in a general case, this is actually unwanted noise, right? Could be anything. This is unwanted noise, okay? And plus, okay, I want to hear what? I want to hear music, or I want to hear my other people's inside with me with the airplane. But this is something that I want to hear from the headphones. So the headphones gonna give me that, but I actually, it's really hard to listen to you guys. It's really hard to listen to the music because I got this annoying sound. So what's gonna happen is that inside your headphones, there's a microphone, a really microphone in the headphones. And this microphone records this thing and deciding to produce a new, actually playing another music, not the one that you want to hear, another one by its own. And the goal of this one is actually to kill this one. Do you understand? He said, my mission, it's like standing like this. My mission is to kill the unwanted noise in the environment. I'm gonna use the microphone of the headphones and gonna create a waveform that's gonna actually kill this bastard. That's the idea. This is the concept, okay? Now you got the concept. So this one is gonna be also a wave phenomenon, right? So let's write each one of them. So this is the idea. And for simplicity, I didn't press the play button, okay? I didn't press play button, not yet, okay? it's just gonna be only additive to our solution. It's not gonna change anything. So I'm not pressing play. I just want to put the headphones and cancel out the engine. That's all I want. I want to hear sound of silence, okay? Nothing else. Perfect. And I'm going back to this board. So let's open up everything, okay? So let's write explicitly what we have. So we have this capital F, right? And this one is equal to F1 plus F2. And we know F1. What is F1? F1 is the amplitude sinus K, right? X minus Vt, right? Plus V1, okay? And I'm gonna produce with F2. I wanna produce a waveform that's gonna actually kill it. So I'm gonna add, I wanna cancel the same amplitude, right? So I'm gonna use the same amplitude. I'm gonna use also sinus. It doesn't matter if it's a sinusoid, of course, because phi can always fix it. It's gonna, if I wanna kill it, for example, if you have, I don't know, birds that's flying here, so you wanna kill it in the same frequency, right? In the same manner. So, K, really weird example, forget about it, I don't know. Minus Vt plus V2. So the only difference between this one and this one is that I don't know what to do with this. I'm gonna record this sound and play it, but I don't know what this V is. So let's sound them up and see what we got, okay? So we're gonna sound them up. You know how to sound sinus? It's really easy to remember. You have A and A, right? So sinus is like this, right? And so you add another one. So the amplitude is twice, okay? If you're gonna sign, let's do sinus theta and sinus phi, okay? You're gonna want to sound them up. It's 2A sinus. You see me on the camera? Good. Good. 2A sinus, the average between them, okay? Multiplied by cosines, half the distance between them, right? Phi over 2. Okay? That's it. Really easy to remember. Okay? Really straightforward. So let's do a 2A, and then you say, shit, dude, what you actually doing? You're amplifying the noise. Not what we wanted, but wait, trust me. Sinus. So this is gonna be the average between them. So I'm gonna sum this one with this one and divide it by 2. So it's gonna give us K, X minus Vt, because we have this, the two of them, divided by 2, multiplied by 2, it's the same. So 2 divided by 2 is 1. Plus, we have the average of phi. 2 divided by 2. Right? Sorry, cosines. No, this one is 2. Okay? This is the first term, and you multiply by what? Cosines, right? And what we have on the cosines? So this minus this divided by 2. So this term and this term are actually dying out, you see? So this one and this one are going to die out, and we stay only with the difference in the phase. Phi1 minus Phi2 divided by 2. Now I want you to look at this stuff, okay? What we have here, a crazy thing. It's changing in space. It's changing in time. You look now, it's changing. You look now, it's changing. You look now, it's changing. It's changing. This creature is changing, right? Not nice at all. But it's multiplied by what? Look at this. Look how cute it is. You see, there's nothing here. There's Phi1, which is given. This is the engine doing its own shit, right? And I got Phi2, which I can decide. I'm gonna make a science, I'm gonna make the cosines, or I'm gonna make whatever I want. So if we can make this one 0, think about it. If I can make this one is 0, what's it gonna do to this thing? Gonna kill it, right? Gonna hunt it down, right? So when this term is actually equal to 0, let's draw cosines. So this is the cosines, and cosines is what is starting the strongest, and then it's dying out. So it's looking at this, right? And it's also a mirror function, right? This axis is like a mirror function. It's happened to both ways. This is pi over 2, right? This is what? 3 pi over 2. And this one is 5 pi over 2, right? So in general, every odd number divided by 2 multiplied by pi gonna give me 0. You see this pattern going on, right? So how do we write odd number in math, you know? What? No, let's focus on that a little bit. So I'm gonna give you really easy. How I do even? 2n. 2n, it must be even. It's twice n, I can divide always by 2, right? So, and let's go back to this board. So if I want to do an even number, I just multiply by some, n equal 0, 1, 2, 3, whatever I want. But if I want my number to be even, I'm just going to say 2n. That's it. And if I want an odd number, what I need to do, I need to take the even number and fuck it up. That's what I need to do. That's all. Fuck it up. 2n, you are even. Fuck you. That's it. Right? You got it? You got a concept? Perfect. Huh? To be plus, it will be minus. Never mind. So I'm gonna end up where? Minus pi over 2. It's gonna be also 0. I don't care. This is gonna give me an odd number. Minus 5, it's an odd number. Okay? So and what I need phi over 1. The phi, let's call it delta phi. Okay? The change between the phi from the environment, the unwanted noise, and phi that I'm producing. I'm in charge, right? Perfect. So this divided by 2 must be equal to what? Odd number. This is my odd number. Multiplied by pi, divided by 2, right? So I actually want this one to be equal to this one. And that's it. That's all I need to satisfy to kill it down. You understand the concept? So this is really cool, okay? So I'm gonna ask you another question. Let's not take my example in the airplane when I was in the military service, but let's talk about other scenario. Let's say that I'm a spy. I'm a spy going around and I want to listen what's going on in the other door. So I'm taking my spy microphone, put it here, and I want to hear what's actually going on the other side. So what's going on here? Let's draw this one. This is another question. Guys, think if I want to kill it down, that's what I need to do. Okay, really important. Okay, so I'm going to clean this one. So now I want to do a spy microphone. Okay, spy, headphones, microphones, it's the same thing for me right now. Headphones, right? So what I actually want to hear, I want to hear F1 louder. I want to do the same thing, but this time I want this one to encourage this one to be strong, right? That's what I want to do. So how I can do it? So I want you to look back in our equation. It's going to be the same math. It's the same concept, okay? Take me to the board. I do a Michael Jackson. Okay, got it? Okay, so this is the environment. This is the people that I want to spy after them, to see what's actually they're talking in this room. It's really important. And I want this one to actually increase the volume, to increase the noise that I'm hearing, right? Not to cancel it out. Okay? So I'm looking here and I said, oh, fuck. This creature, it's a monster. It's changing in X. It's changing it. What do you mean changing in X? If I'm moving my microphone on the door, it's going to change the location. Okay? If it's changing in time, they're talking. It's changing all the time, right? So this is a monster. I don't want to deal with it. Look at this. If I can make this one, I'm going to get the same thing with 2A, stronger. And I'm going to hear it maybe with the delay, okay, because of this speed, right? It maybe going to be a delay. They say, hey, what's up? And I said, hey, what's up? Okay, I can hear this. But if I can make this one, I'm gonna close the div. So let's look here and I see, oh, here 0 is 1. I don't care to have -1, it's the same for me. Here this is 0, this is 5, right? This is this is 2 pi, right? Right? So what actually the pattern that I see? That I just, and here is 3 pi. So I just need to be a whole number and continue and be multiplied by pi. So back to this board. So my actually thing we're gonna satisfy the SPI headphones rule is the delta phi divided by 2 gonna be general n, whatever n that I want, multiplied by 5. That's it. That's it. And then I'm gonna have a SPI tool. Okay? So I understand the concept? This was the idea. Okay, perfect. So we finished this question, and I want to tell you that these devices are wonderful, working really well. Where is the problem? The problem is if the frequency, where is the frequency here? So frequency is really, if it's high frequency, it's really hard to follow. Okay? Okay, high frequency, it's also hard, okay, to follow. Okay, because there's really speed changes and the active headphones want really to follow it up and it's really high, it's really hard. But if it's a low frequency, easy peasy, okay? Not hard at all, and this device working super well. And maybe you hear, I don't know, for example, you know that all the effect, when you're talking about music, that suddenly you have only, for example, Queen's song, only Freddie Mercury singing, without the band. How do you do it? They understand what is the drums and play the drums with this shift in the phase and cancel out the drums, then cancel out the bass, then cancel out, and then leave only with Freddie voice. So, but it's not an easy task to do. So why we actually took this break and talked about waves? So see light, if you're gonna take, forget about light, but if you're gonna take all the equations that we have so far, I mean, all Maxwell equations, all the 4 of them, and that's what Maxwell was trying to do. We're trying, let's draw it out, okay? So this is the motivation to the next chapter. So Maxwell said, we know stuff. We know Gauss's law. We know that the integral on EDA equal Q in A, and we know also the magnetic Gauss, right? He said that this one I know it's 0. And we know also the loop, this area integral. And we know the loop integral, EDL, right, is equal to the change in phi p dt minus Lenz's law. And I also know that Ampere's law, DL, I know the DL, PDL is mu0 I penetrate. I know this stuff, okay? And when he drew all this stuff out, he saw that, hey, something is weird. Because on the loop integral, I see dependency between magnetic and electric, and here I don't see this dependency. So first of all, you understand we have here error. We have some mistake, error. And I'm funny to write error like this. Okay, so there is the error here. And he understands that there's a missing part here. So he fixed this one. And after he fixed this one, he asked, does all equations, all these equations can go to be one equation? I'm going to be super fast. If I'm going to do that, put all these laws inside one equation, I'm going to be superstar. That's what he said, let's do it. And then he did that, and what he discovered? He discovered that all of these equations can be one equation. Crazy. You want to see this equation? That's all of them together. All of them together. He did it, and he found this one. Look careful. Look careful. Okay? I'm changing in history. The magnetic field changing twice in time equal to a constant square derivative of b divided by x squared. He said, I have another equation. I have e, and then you get a goosebump, you know? You have to chill and say, oh fucking shit. Oh fucking shit. What do we see here? What do we see here? It's a wave phenomena. Electric field and magnetic fields are actually a wave phenomena. And you want to know what is this constant? Huh? This is a constant. What this one is actually the speed of light. And then he said, crap, light is electromagnetism. Fuck! Nobody knew it. There was no experiment that said that at all. And then you understand he must do an experiment to show that light is actually electromagnetic wave. Got it? So this is the sweet victory of Maxwell. And this is the reason he's so famous, okay? Because he came to realize that that light is actually magnetic phenomena, electric phenomena, combined to propagate as a wave together. And actually, it's going to be like this. You're going to see it in the next chapter. One electric, one magnetic, and it's propagate in the speed of light to you. So this is a sweet victory of Maxwell. And with this excitement, I want to finish the class and make you curious about what you're going to do next time. So bye, guys. See you next time. If you have any question, feel free to ask, feel free to comment, feel free to do a like if you love this tutorial, and go ahead, I'm with you. Thank you very much, guys. See ya.